Assalamualaikum students. Today we will solve the MCQs of chapter 4 gases. So the first MCQs is, when compared at the same temperature and pressure, which one among the following properties have the same value of H2, N2 and O2? So we know that according to kinetic molecular theory says that when we have different gases at same temperature and pressure, then the average kinetic molecular energy of that different gases will be same. So here option C is correct. Now read again. When compared with the same, we have different gases H2, N2 and O2. So when the pressure and temperature are same, then their kinetic molecular energy will be same, average kinetic molecular energy. So option C is correct. The next MCQs. A container with a porous wall is filled with one mole each of He and H2, nitrogen and carbon dioxide. Which one of these gases will take the least time to diffuse out of the container? So here, taking least time means that the rate of which gas will be greater. And here we know that rate is inversely proportional to the under root of molecular mass of gas. So we have 4 different gases and a porous wall container. So which gas will diffuse first? Which gas will take least time? Or which gas have greater rate? So we know that helium is equal to 4 molecular mass, hydrogen is 2, N2 is 28 and carbon dioxide is 44. So H2 will take least time to diffuse out of the container. Next MCQs. Air is a mixture of N2, O2, argon, carbon dioxide. The total pressure of air is 760 mm of Hg. So gas having highest partial pressure in air is, here we know that the nitrogen is 78% present in air. We know that nitrogen is in greater amount, so the partial pressure of nitrogen will be obviously greater. So here total pressure is 760 mm of Hg, okay, and N2O2 are given. So we know that nitrogen is in greater amount, so the partial pressure of nitrogen will be greater. Next, van der Waals constant A depend upon the intermolecular forces among the molecules. Comparing the following gases, which one have the highest value of A? Here we know that A is directly proportional to the intermolecular gases of gas. Intermolecular gases, okay? So here we know that N2 is non-polar, okay? H2 is also non-polar, and helium is an inert gas, so it behave ideally in most cases, okay? So here we left with methane. We know that methane is non-polar as a whole, but if we look at its structure, here let's suppose I take this bond. Methane has zero dipole moment, but its bond moment is non-zero, okay? So when its bond moment is non-zero, so we can consider that up to a certain extent it has polarity, okay? In molecule, up to a certain extent it has polarity, and also it has a greater size. So methane has the highest value of A, okay? Among these, look at its non-polar, there is no bond moment also. Bond moment is also 0. Here bond moment is 0. Helium is inert, so it behave ideally, okay, in most cases, and we left with methane, so option D is correct. Next one, a student found that the critical temperature of sulfur dioxide is very high as compared to carbon dioxide. Dr. Khan told him that the reason is, so in MCQs we have given that 2 gases are given, sulfur dioxide and carbon dioxide, and here we know that carbon dioxide has 0 dipole moment, okay? Dipole moment of carbon dioxide is 0, while sulfur dioxide has non-zero dipole moment, okay? So the polarity of sulfur dioxide will be present. So the reason is sulfur dioxide is polar, and we know that polarity is directly proportional to critical temperature. So what the student has said, that sulfur dioxide has greater critical temperature than carbon dioxide. What is the reason? So Dr. Khan told him that polarity of sulfur dioxide is greater than carbon dioxide, as carbon dioxide is non-polar, okay? Next one. A latecomer student who was standing outside of the lecture room, he heard that few words of Dr. Khan. So a latecomer was standing outside and he heard few words from teacher that in lecture, flat screen of television, neon sign and sun. The first idea that may come to the latecomer in mind. So he get the idea that the teacher is talking about the plasma. Okay, he is giving a lecture about plasma. Next one. When you read out the topic of plasma in your book, you will find that plasma is used in the flat screen of television, neon sign, and the sun. Sun also contain plasma, okay? Next one. Keeping the temperature of gas constant. If the volume of gas is 10 liter at 1 atm pressure, then its volume will be 25 liter at. So let's solve this. Here we have given that at 1 atm pressure, the volume of gas is 10 liter. So at what atm pressure, the volume will be 2.5 liter. So here we will use that P1 V1 is equal to P2 V2, okay, Boyle's law. Here we have given P1 as 10 liter and V1 as 1 atm. Sorry, we have given the V1 as 10 liter and P1 as 1 atm. Okay, and P2 we have given V2 at 2.5 liter is, and P2 is unknown. Okay, here let's write P2. Okay, P2 is unknown. Now here write it at P2 and P2. Okay, now what is 10 liter multiplied by 1 atm? So 10 liter atm, and take this and write it here in division. Okay, 2.5 liter. So cut the liter and 2.54s are 10 atm. Okay, when we do cutting here, 2.51s are 2.5 and 2.54s are 10. So the answer is 4 atm. B option is correct. Next one. If the pressure of a gas is kept constant, its volume increases from 25 liter to 50 liter. The corresponding increase in its temperature is from 25 degrees C to. So here Charles' law can be applied. Okay, so we have given that volume increases from 25 liter to 50 liter. Okay, and the temperature increases from 27 degrees C to dash. So we have to find the T2, temperature at which the volume of gas is 50 liter. Okay, we have to find the temperature at which the volume of gas is 50 liter. Now let's find the temperature. Here we know that V1 divided by T1 is equal to V2 divided by T2. So what we have to do is we have to find T2. Okay, we have to find T2, but first of all we have to convert the centigrade into Kelvin. So how we will convert it? Kelvin, write centigrade temperature plus 273. Okay, you should add 273 with 27, so we will get 300 Kelvin. So next come to the MCQ. So we have to find the T2. What we will do that, bring T2 from here and write it there. Okay, in place of V2, and bring V1 in place of T2. Okay, what I repeat, that bring T2 and place it here in the place of V1. Okay, and take V1 and place it here. Okay, in the place of T2. Now what you have to do with T1, take this and place it here. Okay, with V2 like this. T2, V2 multiplied by T1 divided by V1. Okay, I hope you understand this, that V1 will be in the place of T2 and exchange it, like bring T2 here and V1 here. Okay, we can exchange it. Okay, and bring T1 there with V2 like this. Okay, now put the values. T2, V2 is equal to 50 liter and T1 is 300 Kelvin and V1 is what, 25 liter. Okay, now 25 ones are 25 and here you put 2. Okay, 2 multiplied 300 is equal to 600 Kelvin. But look at the options. We have given the options in centigrade. So what you have to do is convert again the Kelvin into centigrade. Now take the Kelvin temperature and minus 273. Okay, so you will get the temperature in centigrade. And the answer is 327 degrees C. Now keep one thing in your mind, that this one step is very important to get the step. Okay, you can't skip this one. Okay, and also this one. Like you will be thinking that we will directly put the degree C here and we will get the answer. No, it's wrong. You can't put directly the degree C, because in Charles' law the temperature is always in Kelvin, so you have to convert it into Kelvin. Now the next MCQ. At constant temperature and pressure, the volume of gas is directly proportional to number of moles. It's a statement of Avogadro's law. Okay, Avogadro's law, that at constant temperature and pressure or same temperature and pressure, the volume of gas is directly proportional to number of moles. Now come to the next MCQ. The next one is, which one of the following statement is true for an equimolar mixture of hydrogen and oxygen? Now we have given the equimolar hydrogen and oxygen, like for example 2 moles of hydrogen or 2 moles of oxygen, or 3 moles of hydrogen and 3 moles of oxygen. Okay, we have given the equimolar. So option A is partial pressure of oxygen will be greater than that of hydrogen. It's wrong. The partial pressure of hydrogen will be greater than oxygen. It's also wrong. Both cases will have equal partial pressure. It's correct. Okay, we know that the partial pressure is the function of number of particles. Okay, when we have same moles, it means that we have same number of particles, which means that the partial pressure will be equal. I have also proved this. Like look at this, we have same number of equal number of moles, hydrogen 2 moles and oxygen 2 moles. Let's find the partial pressure of hydrogen. Okay, so we know that partial pressure of hydrogen is equal to x dot total pressure. Okay, what is x? It's the number of moles of a specific gas divided by total number of moles. So specific gas 2 moles and total number 4 moles multiplied by total pressure. So in place of total pressure, when we don't have given the specific pressure, we put simply 1. Okay, now here we get the answer of 0.5 atm. Now the partial pressure of oxygen is, we know that partial pressure of oxygen is 2 mole, okay, and total pressure is 4 mole, and multiply by 1 because we don't have a specific total pressure, so we put here 1 and multiply, so we get 0.5 atm. Look, both have same partial pressure. Okay, now the option C is correct. Option D, nothing can be said about the partial pressure without knowing the temperature. So it's also wrong. We can find it without knowing the temperature of mixture. Next, Dr. Khan told his student that Dalton's law of partial pressure is applicable to all of the following mixture except. So we know that Dalton's law of partial pressure is only applicable to gases. Okay, only applicable to gases. But here, look at the option D. We have given hydrogen chloride, which is liquid. So option D is correct. Here look at this, application to all of the following mixture, applicable to all of the following mixture except, so except is this hydrogen chloride. Okay, next one, which of the following relationship is correct? Now look at the option, PV divided by nRT is equal to 1. So let the nRT be, let's bring the nRT here. Okay, PV is equal to, when I bring the nRT on the other side of the equation, so it will become nRT. Okay, so now look the next question, next option, PV is equal to, PV divided by nRT is equal to 0. Now when I bring it here, then what will happen? Look, 0 multiplied by nRT, so I will get the answer as PV is equal to 0. Okay, now look at the next one, PV is equal to constant multiplied by nRT, and both end. Now look at this, which one equation is correct? We know that this equation is correct for ideal case equation. Okay, when we put the PV is divided by nRT is equal to 1, so it become ideal gas equation, and we can also write it like PV divided by nRT is equal to Z. Okay, Z is the compressibility factor. Compressibility factor, when we get Z is equal to 1, it means that the gas is ideal. Okay, the gas is ideal, and here we will get the answer like this. Okay, when we put Z is equal to 1, here look at this, Z is equal to 1. In place of Z we put 1. So we will get this equation, which means that the gas is ideal. So option A is correct. Now look at the next one. All of the following gases will behave ideally at 20 degrees C except. So look at the options. Option A, B, C are non-polar. Okay, they all are non-polar. There is no dipole moment as well as bond moment, and they all are non-polar because same atom combined to form molecule. They are homoatomic molecule. Now look at the hydrogen chloride HCl. We know that hydrogen chloride partial positive here and partial negative here. So polarity is found there. So out of the following gas, it will not behave ideally. Okay, non-polar gas do not, polar gases do not behave ideally. Okay, so the correct is this one. All of the following gases will behave ideally at 20 degrees C except hydrogen chloride. Okay, because it's a polar and it has a value greater. Okay, so it's a real, it will behave as real gas. Next, at the same temperature and pressure, most ideal gas among the following is. Now here keep one thing in your mind, that inert gases mostly behave ideally. Okay, what? Inert gases behave ideally, mostly. Okay, mostly behave ideally. Okay, now this one is not inert, this one is also not inert because there is a little bond movement is found here. Okay, now come to the C and D. Here we know that whenever we have low polarity, intermolecular forces are low, then that gas will behave ideally. Okay, when like here we know that A is directly proportional to polarity or intermolecular force. We know that, but whenever A is greater, the gas will behave as a real gas. Okay, the gas will behave as a real gas. Now when the polarity is low or the intermolecular forces is very weak, then the gas will behave ideally. Okay, so look at these two. We know that there is London dispersion force. Okay, London dispersion force is found in helium, so it means that the intermolecular forces are very much weak. So option D is correct. Okay, the behavior of a gas is non-ideal at. So look at here. What is an ideal gas or what is an real gas? A real gas is that one which contain intermolecular forces are which have volume of gas, okay, actual volume of gas, which have actual volume of gas, okay. These both properties are of real gas, okay. These properties are found in real gas. Now what is ideal gas? The ideal gas is the one which have no intermolecular force, and the ideal gas is the one which have negligible volume of gas, okay, negligible volume of gas. This is called ideal gas. So the intermolecular forces will be negligible when the temperature is very high and the pressure is very low. Then what will happen? Molecule will behave ideally, okay. But when the temperature is very low and the pressure is very high, then what will happen? When we get the high pressure, so the gas molecule will come closer to each other, and there will be found the intermolecular forces among the gas molecule. And when the temperature is very low, then the kinetic energy of the gas molecule will be low. That's why they will come closer to each other. And when they come closer to each other, there will be found intermolecular forces, as well as the volume of the gas can be found there, okay. The volume of the gas will be observed there. So B option is correct. Gas behave non-ideal at low temperature and high pressure, because at low temperature and high pressure the intermolecular forces are found in the actual volume of gas. What is the actual volume of gas? Look at here. Look at here. The actual volume of gas is like this. These are the molecules of gas, so their actual volume is this, okay, this one. So the actual molecule of gas will be observed at high pressure and low temperature. Now the next one. Which one among the following postulate of kinetic molecular theory need to be correction at high pressure? Now, if we don't have this one, okay, high pressure, if we are not given the high pressure, then what two corrections will need, okay? Two postulates will need correction if we don't have given the high pressure, okay. The one is inter-attraction force or repulsion force, and the next one is volume of gas. This one, A and D, would be need correction. But we have given the high pressure. Now look what is meant by high pressure here in this MCQs. Now look, it's a container. When the pressure of molecules, these are the molecule of gases, okay. When the pressure of molecules of gases are very high, okay, when the pressure is very high, then the molecules will not look at the intermolecular forces, okay. The molecule will not care about the intermolecular forces, and they will exert their pressure with a high speed, okay. We know that the real molecule have pressure which is the real molecule have intermolecular forces. Real gas have intermolecular forces, we know that. So intermolecular forces will attract, like here this one molecule, we will consider this one. Here, if this molecule will exert pressure on the container, then the next molecule will push back this one, okay. This one molecule will push it back because of the intermolecular forces, like this one. Look at this. We have two molecules. This is A and this is B, okay. In real gas there is intermolecular forces. When this one molecule will apply pressure on the container, then the B molecule will resist it, and due to intermolecular forces it will push this molecule back toward itself, and in this case the pressure will be pressure will be a little low. Now here what we have given in MCQ, that the pressure is very high. When the pressure is very high, look, when the pressure is very high, then the A molecule will not care about the B molecule. It will not care that B molecule is exerting pressure on it, okay. A molecule will not care about this intermolecular force, so it will exert its high pressure on the container. Now what we have, real gas formula is P plus A N square. The intermolecular forces is negligible, okay. When this molecule don't care about the intermolecular forces of P molecule, then this expression shows intermolecular force, this one expression, okay. So it will become 0, and the equation at high pressure would be like this. Okay. So what is the ideal gas equation? Ideal gas equation is PV equal to nRT. This is ideal gas equation. So compare these two equations. Now compare these two equations. What is this? So when we compare these two equations, now look at this. Which correction is required in ideal gas equation? Which correction is required? Here volume correction is only required. Only volume correction is required. Okay. Look, this is real gas, okay, that is real gas equation at high pressure. At high pressure, so ideal gas required which correction? Ideal gas required only volume correction because the pressure is same at high pressure. At high pressure, this P term compared with ideal case equation, they both are same, okay? Only correction is required for volume. Now look at the options. Look at the option. So this one is negligible, so this one is incorrect. Force of gravity has no effect on the motion of gas. This one is also. Actually, the suitable is option D. Actual molecule of gas is actual volume of gas is negligible as compared with its occupied volume. Now look at this. Okay, so this one is suitable for high pressure correction. Now, and this one and this one do not need correction. Okay, only this one need correction. Option D. At high pressure, option D need correction. If there was low pressure, at low pressure, then option A would be correct. Okay, option A would be correct for low pressure. Next one. Well, before going to the next one, I want to make you clear at low pressure. What will happen at low pressure? So, at low pressure, what will happen? Look at this. At low pressure, the molecule will do not exert much pressure on the walls of container. Okay, let's suppose it's molecule A and it's B. It will not exert high pressure on the wall of container. Then next, what will happen? These intermolecular forces will be dominant. Okay, these intermolecular forces will be dominant. But I take this like, so when the intermolecular forces are dominant among the molecules, so this actual volume will be negligible. This actual volume will be negligible, okay, as compared to this free volume. Okay, now think about it. When the intermolecular forces are dominant, the molecule will be very closer to each other, and then when the molecule is very closer, then what will happen? The free space will be very much and the actual volume will be negligible. Okay, I hope you people understand. If you don't get this, then write in comment section. Okay, now what will happen? We know that real gas equation P plus A n square divided by V square. Okay, and V minus NV is equal to nRT. So when the volume is negligible, then it means that this term will be 0 because this term shows about the actual volume of gas. So the equation would be like this: A n square divided by V square, and V is equal to nRT. Okay, now it's real gas equation at low pressure. Okay, real gas equation at low pressure. Now look at this. What is ideal gas equation? We know that PV is equal to nRT. Now compare these both equation as, like, look at there. At low pressure, the real gas and the ideal gas have same volume. Okay, the real gas and ideal gas showing the same volume at low pressure. But here the correction is needing in pressure. Okay, where the correction is needed? The correction is needed here in the place of this P. Okay, there correction is needed. So what will happen at low pressure? The kinetic molecular theory need correction in the pressure. Okay, so this pressure represent, like this term represent intermolecular forces. Okay, intermolecular forces are present. Okay, this term represent intermolecular forces. So at low pressure, the ideal gas equation need correction at pressure. Okay, only need correction at pressure. So when, look at this, pressure is the function of intermolecular forces. Okay, pressure is the function of intermolecular forces. So in turn, it will need correction in option A. Look at this. There are no force of attraction or repulsion among the gas molecules. So at low pressure, correction would be needed in this statement. Okay, now next one. In van der Waals equation, the term n square A divided by V shows the attraction forces between the molecule, which means that the attractive forces is not 0. Shows that the attractive forces of molecule is not 0. Okay, what does it mean? That we know that when the attractive forces are non-zero, then the pressure is need correction. Okay, so it shows non-zero attractive forces. Now 18 number, comparing the polarity of molecule and molar, which one among the following gases have highest critical temperature? We know that A is directly proportional to intermolecular force and A is directly proportional to critical temperature, which means that intermolecular forces is directly proportional to critical temperature. Okay, now this one is non-polar molecule, this one is also non-polar molecule. Okay, and this one is also non-polar molecule, but option C is correct. It is polar molecule, which means that it have the highest critical temperature. Okay, it has the highest critical temperature. Look at the carbon dioxide. It's like carbon dioxide. Okay, so here is the bond movement like this and bond movement like this. these two bond movement will cancel the effect of each other and the molecule in turn will be non-polar. Okay, so and SO2 like this, sorry, it's SO2, so it means that they will not cancel the effect of each other and they have the dipole moment, which means that it is a polar molecule. Okay, so it have the highest critical temperature. Next one, the plasma produced from nitrogen and oxygen gas. Now keep this in mind that plasma as a whole is a neutral. Okay, it has no charge. Plasma as a whole is neutral. This is in your topic, in your book. It is present in your book in the plasma topic. Okay, just read this one. Here it is present that plasma as a whole is neutral. Now we will do the remaining MCQs in the next video. Allah Hafiz.